Hi, fellow geochemists and geochemistry enthusiasts. Welcome to Geochemist Tea, the only podcast for people who love geochemistry with a side of tea. Our mission is to inspire and to shed light on the topics not fancy enough to talk about at a conference, but important to delve into. I'm your host, Sam Schur, and this week we're talking with Duncan McLeish about colloidal transport of gold. And for the link to Duncan's article, head to our website at www.geochemisty.com. Duncan is a postdoc in Willie William Jones's research group at McGill University. Duncan, welcome to Geochemistry.
Thanks a lot, Sam. Thanks for having me. It's great to be here.
I first met Duncan when he was giving a really fascinating talk on the colloidal transport of gold at the Brucejack mine, Canada. And after watching, I immediately reached out and begged for him to share his research here at Geochemistry. Duncan, can you talk to our young listeners about your career path and how you wound up at McGill and why that's special?
Yeah, for sure. I guess it's a good way to introduce myself, and I guess a natural place to start would be for Earth Sciences would be my undergraduate degree. So I did an undergrad in Earth Sciences at Dalhousie University in Halifax, Nova Scotia. That was way back in 2000. I was there 2004 to 2008, and originally, I was not really. I actually don't even think I took a undergrad course in geochemistry. I did some, requisite chemistry, but I did an honors project in structural metamorphic geology, looking at some high-grade granulite gneiss rocks in Georgian Bay, Parry Sound in Ontario, for my supervisor there, who was actually just passed away, unfortunately. His name was Dr. Nick Culshaw. That kind of there was some thermobarometry involved, so looking at estimating pressures and temperatures from metamorphic mineral assemblages. So that kind of, there was a little kind of teaser sideways introduction to aspects of geochemistry, more mineral chemistry. But there was no kind of economic, there was no economic part of that. But after I graduated, I was really interested in field mapping, and I got a job with the Nova Scotia Survey and worked there for a summer. And that was great. I did bedrock regional mapping around Halifax, so it was very urban. It's something that we think of doing field mapping either flying in helicopters or working, in these kind of great open landscapes. But that was driving around in Nova Scotia DNR truck, knocking on people's doors, asking them if they could look at outcrops in their backyards, and you were able to have lunch at Tim Hortons rather than on the side of a mountaintop. So that was kind of cool, just as an aside. But long story short, on the earlier part, I basically was looking for work after that. That was just a summer position, and there was an opportunity to move out west and actually work for the BC Geological Survey as a field assistant. So I moved out to Victoria for that. That eventually led to a master's at the University of Victoria. I was doing some field mapping in the northeast part of the BC foreland belts in the Rocky Mountains. It so happens that there's a line of carbonatite intrusions that basically are found right along the western margin of the foreland belt. And there was a prof at the University of Victoria by the name of Stephen Johnston who was interested in these, just asking a simple question, why do we have carbonatites in this passive margin stratigraphy that anyone who's been to the Rockies knows, the beautiful limestone ridge lines and exposures, and then all of a sudden there's this line of intrusive rocks. So that was my master's, and I kind of got involved in economic geology because the carbonatite that I studied for my master's, the alley carbonatite, was being explored by a company, Taseko Mines, for its niobium. And so that was kind of, we were originally kind of just totally independent from the exploration project that was going on there, but just naturally, because we were mapping the carbonatite, they were drilling it. It kind of evolved into I got a summer position there eventually, and got involved in mineral exploration. So that was kind of my almost 10 years later sideways link into the exploration side of geochemistry, and then after that, so that was, I finished that in 2012, I believe, and then I kind of, Taseko, the mining company, was based in Vancouver, so I moved to Vancouver. I worked for them and their kind of parent company by the name of Hunter Dickinson. So I got to work all over British Columbia on a variety of different mineral projects, exploration projects that I kind of won't go through all of them, but I did. I got to work at a mine, Gibraltar, which is Canada's second largest porphyry mine after Highland Valley. So that was pretty cool. Through all those projects, I was basically being exposed to, the very applied sides of exploration and geochemistry in terms of I was getting interested in aspects of how do we leverage it to basically help us, find whatever the target is that we're looking for. So that those were exciting years, but they were up and down years in terms of anybody who's been around. Either I was a consultant for a bit. I was working for these companies directly as an employee for a bit, but 2011 things were kind of good, and then things basically up until I started my PhD in 2015, things were kind of on a downward trajectory in terms of market conditions. Metal prices and things like that. So it was pretty rocky, and part of the reason I decided to do a PhD, among a lot of things, was just that, I got kind of worn out after 3 or 4 years of doing camp jobs, doing drill core logging, and I kind of wanted to. I really enjoyed the kind of science behind it, and I wanted to kind of get to know ore deposits better at a kind of higher level. I guess how did I end up with Willie specifically? There's try and make this story as short as possible. So I was working through, I mentioned the Hunter Dickinson group of companies. They had a small, one of their juniors was called Brigade Exploration, and they were exploring a small porphyry called Tennyson Porphyry, which is close to Brucejack. This is in the Golden Triangle of Northwest British Columbia. Brucejack is where my PhD was based, and a little where the paper I'll be talking about today, all the research was done. So we were kind of one of these satellite exploration projects. Brucejack had just hit their first bonanza, 10,000 plus gram per ton intersections of visible electrum, and everybody was super excited. The stock price was doing really well. Pretium, the parent company, and it was kind of the big success story in the Golden Triangle. I wasn't part of that back then, and I was working for Brigade, but we actually had a camp in just north of the town of Stewart. Anybody who's been to Northwest BC will know Stewart. In the camp, basically it was a fly camp for our porphyry exploration project, but Pretium was flying. Anybody who's seen pictures of Brucejack knows it's basically up in the high alpines surrounded by glaciers, and at the time it was road inaccessible. So they had to fly in this basically advanced equipment to develop the mine, because at the time they're doing a bulk sample, all this kind of stuff. stuff with no road. So they were flying in heavy equipment from an airstrip they had there. And I basically got to meet a lot of or at least a portion of their crew, and said, hey, Brucejack is an awesome deposit. I saw pictures of some of the gold intercepts that they were drilling there, and I was just blown away. Here I was on this porphyry exploration job, and we were basically, as with a lot of porphyries, there's no visible gold. I'm straining my eyes just to see small bits of chalcopyrite in veins, and these guys are walking around with basically nuggets of gold in their core samples that they're displaying, flying out of sight to go bring to Vancouver and display. And I just thought it was spectacular. I guess you could say I caught the gold bug there. So I was basically looking for a PhD project at the time, and I knew there was a fellow by the name of Nick Herrikhausen who did a master's here at McGill. He was the master's student, I believe, at Brucejack, and he kind of helped me out a bit, get to know the company. Warwick Board was the name of the chief geologist at the time at Pretium, and I basically brought him. I met him in Vancouver, and I noticed that he had some of at least our supervisors, Willie Williams-Jones, papers taped to his office wall. Just the first page of the papers with the abstract, and he's like, well, this guy, is really into gold solubility, figuring out how do we form super high grade veins of gold, and how do we explore for them if we understand how we can form them. So I was like, well, this is I better meet this guy Willie, so I was actually at GACMAC. I think it was the year before. It was in Ottawa, and Willie got the Logan Medal. So I had a chance to meet him there. It's funny, all these kind of just chance encounters, and just because I had that contact information, I basically almost built the PhD project myself. I don't want to take complete credit for it, but I introduced him to Warwick, said, can we do something here? We wrote an NSERC CRD grant together. So that actually took like a whole year to set up. And then in 2015, I moved to Montreal from Vancouver and started my PhD. And here I am 7 years later. I've just defended it.
That's such a cool story.
Thanks, Sam. Wow. I hope that wasn't too long.
No. Honestly, and this is my opinion going out there to the world, I think that a lot of these PhDs that I've heard of through the many years of being in industry is just that they're so cookie cutter, and they're so set up, and it's just that why are we even doing PhDs anymore when they don't really have meaning? I know that there's this bunch in Australia where people just go and they'll study these little volcanoes outside of one of the towns in Australia. People just pick one of the old volcano, the cinder cone, and they'll do a PhD on that, and it just it just happens over and over again. And it's just like, what is the learning there? What is your question? And we've lost the spirit of the PhD. And this gives me a lot of renewed faith in the PhD. And I think that's just a really, really neat story about how this was all set up, and how your questions probably continue to evolve as you did it. But that's the whole spirit of the PhD. So very cool. Thanks for sharing.
Yeah, I guess just to sum up your original question was, what can young listeners at home take home? I think it's really, and not to poo-poo. I'd say most of PhDs I've seen, my fellow students, they have defined project. A supervisor has this question. They've gotten funding from either a government agency or a company to go hire go get a PhD student and tackle this. I guess my story is the opposite, and just to encourage people, if you're really interested, if you're stuck on a drill program somewhere, I don't know what proportion of your listeners are working in industry, but for those that are, or even I guess stuck in an office, maybe processing data for a geochemical company, if there's something you're like, whoa, this is really interesting, and I want to spend more time on it, then I'm allowed to underneath this kind of the nature of industry is it's more rigid, and you have goals and objectives, and then you get a new mandate and it changes, and you're like, well, actually I really like doing that. Don't be afraid to go knock on somebody's door and say, do you think, is there any way I could make a study out of this, make a project out of it? And I think more often than not, you'll be surprised that given the right conditions, people are very supportive for people who bring their own projects, their own ideas, because if you're in the shoes of a supervisor, this person's obviously motivated. They've thought about this enough to want to do it and propose the idea, right? So that kind of removes some of the uncertainty when you have these advertised positions, whether or not this person's really motivated by this.
Super neat. I guess with that, let's transition now into some tea. So what'd you bring for us, and spill it?
Sure. So my tea is a little bit, I guess it's a little bit self-interested in it, because it is related to the paper we're going to talk about for colloidal transport of gold, but really to motivate it, I guess, and it is kind of gossipy. I mean, it's the background of the problem of colloids and how we started looking for it, and this applies to basically, I think, anybody doing science. People have stories of dogma and of going up against some knowledge that is kind of assumed, a priori to be correct. And in the colloidal world, so first of all, I just got to do it. Like, what is a colloid? For those people who didn't have a chance to look at the paper, basically the idea that there's one can form veins of solid gold, or at least locally solid gold nuggets in hydrothermal quartz carbonate veins, by transporting the gold as a colloidal suspension. So solid nanoparticles of gold they have little negative surface charges, and those negative surface charges enable these little particles to maintain a suspension. So that's very different from the 90. I don't know this quantitatively for sure, but I'm going to go out there and say 95% of any geochemistry now, at least applied in mineral exploration, assumes that your metal, regardless if it's gold, copper, and you name your metal, precious or base, is being transported in those hydrothermal veins in the dissolved state, so in solution. So this is really a kind of a fundamentally different way of looking at metal transport to form your ore deposit. That we have these solid particles. Now, where I'm going with this is to kind of talking about dogma. This is the story, and there's lots of stories in science that I find this very interesting, of kind of how people test ideas and how ideas come up. So the idea of colloidal transport is not new. It's certainly our group didn't come up with it at McGill. The modern work is other people looking at colloids. It's not something that anybody alive can take credit for. Really, in economic geology, there's still some debate about who exactly came up with it originally, but definitely Waldemar Lindgren, the father, quote unquote, father of economic geology, one of the founders of the Society of Economic Geologists. He was a big proponent of colloidal transport. So basically forming these ore deposits through transporting metals in suspension rather than in solution. And this kind of comes back then. It was very, we have, if you look at the paper we're going to discuss today, we have the benefit of being able to image things at the nanoscale, so we can actually look for these solid evidence of these solid nanoparticles. Back then, they didn't have any of that, so they basically were looking at textures and wondering, just really speculating at how they could form textures. So the word colloid and colliform, they have a common root. And basically the idea was a lot of these colliform, particularly in lead zinc deposits, you get spectacular colliform textures, not only in, we think of them in quartz, but also in minerals like sphalerite. And there is this idea that these colliform textured minerals formed from a gel, and that gel was basically formed of a suspension of nanoparticles, really to make the kind of short, the long story short. And so there was kind of, for 30 or 40 years, there was a lot of workers in the economic geology community were thinking about ore deposits as forming from colloidal suspensions. And then there was a fellow in the 1960s by the name of Edwin Reuter. I think he was at the USGS. I might be wrong on that. but he basically came out with this paper in economic geology, and it's the title of this paper to kind of show you the weight of these arguments. It basically is the non-colloidal origin of colloform textures in ores. So it was a very strongly worded thesis. This is all, and I don't have time to go into all his arguments against it, but basically that in working in parallel with other workers at the time, which were showing that you could dissolve a lot of metals in the right kind of complexes, so whether it's bisulfide or chloride complexes, not just gold but copper and all this. So people are doing this is all experimental geochemistry. People are having great success in dissolving metals, and basically Reuter did this textural analysis and made all these arguments that says, well, you can form these colloform textures simply by precipitating, by boiling or whatever your precipitating mechanism is, to kind of have these kind of stepwise bands, and it's simply can be explained through dissolution and precipitation. So I guess the end of the T is that this was kind of accepted on a theory based on the theory, but nobody really challenged this until the 1980s and 1970s. There was actually some Soviet workers, so Russians, who were basically still trying to figure out if you could explain some of these textures from colloidal transport. But in America, it wasn't until or I guess the West, a fellow by the name of Jim Saunders wrote a paper that was published in Geology in, I think it was 1990, and that laid out a case again for colloidal transport. And the issue there is it really, the nice thing about transporting gold or any metal as a solid particle is it gets around a huge problem in the solubility world, or the solution world, is the problem of solubility limits. So think of just as a kid, I remember used to be pouring sugar or salt into water. You can, it's fun to take a big heaping tablespoon and dump it in and watch it all go away. But if you keep adding those tablespoons, eventually you're going to reach a solubility limit. You can no longer dissolve any more in that beaker of water, and you'll see basically layers of it depositing all along the bottom of your glass or your beaker or whatever you're doing as your little childhood experiment. But that same problem exists in metal transport, and so metals like gold have very, very low solubility in hydrothermal solutions. And so how do we explain these bonanza ores? In Saunders' case, he was looking at deposits in the southwest US. I believe it was the Sleeper deposit. Our case, Brucejack, if you're transporting these metals as a solid nanoparticle, if they're not dissolved, then you're not bound by all these solubility limits in terms of geochemical models and such. So the important thing is that these guys is to always think critically, I guess, at the basically there's been times throughout, in these different periods where people are making these blanket statements and they get repeated and repeated and repeated in journals that, there is no evidence for colloform textures falling through colloidal transport, and that kind of governs the way of thinking and the teaching. But it is important to ask, where is the evidence for this? And I think, in the 90s, people started asking these critical questions again, and probably in the 80s too. But the nice thing about that time is that we had all of a sudden the ability to image these things. So the advance of transmission electron microscopy to basically go from, on the SEM, we look at things at micron levels, but go down to the nanometer scale and look for evidence. And that's something that we've done in our research, and we've really, kind of built on these suggestions of others, and basically, tested these two groups, because there is nobody's fault, but before we had widespread kind of the ability of TEMs, it was really just taking one group against the other, saying, oh, there's no colloids. The other group saying, oh, it's a great idea to explain these textures. But unless you can image down to that scale, that's the way to test the dogma. So I guess I don't know if that's how gossipy that is, but it's always important in science.
I mean, I think what you did is you brought me some kind of elevated high school Mean Girls, turf war. So, I mean, I like it. This fits into the tea. I like it. It's spanned across decades. I feel it's a very elevated tea that you've brought to us here. But it's very interesting, because unless you spent a lot of time researching and had to go through all the different journals and papers to find stuff for, say, a thesis, why would we, as normal fans of gold and understanders of gold, know this kind of thing? So thanks for bringing that to us here to listen to. No, I think that was really interesting. I always really enjoy what people bring to tea. It's always quite different, people's interpretation of tea time.
Yeah, it's fun. I mean, you give us. I've listened to a few of these podcasts, and there's a lot of leeway in terms of what constitutes tea. So I think that's nice.
Tea's what you make of it.
Exactly.
But it should never be harmful. And so I think we've appreciated all these different groups' work throughout the years. You've let no opinion down, which I think was nice, but you did bring this little turf war to us. So I think that's very interesting. And I think it definitely describes stuff that continues through today. I mean, I've had, even though I only put out for my master's research something that was relatively small in the grand scheme of the world of gold and epithermal, I mean, I've had people approach me with their ideas on how all my research was completely wrong and how the entire group's research was completely wrong. And I was like, thank you for sharing. I'm going to go have another glass of wine now, because I'm not that I wasn't interested in their opinion, but they were a little bit aggressive about it. And I was like, okay, maybe not have this conversation at 10 p.m. at PDAC, please.
No, for sure. I think the important take home of all these, I guess a turf war is a good way to kind of sensationalize it.
Exactly.
Is never be afraid to challenge. If somebody walks up to you and says you're completely wrong, I agree. 10 p.m. at PDAC, probably not the best place to do it.
Exactly.
If you're in the afternoon in front of a poster or something like that, and I'm sure we're not here to be friends. I want to hear the reasons why you think I'm completely wrong. And so I guess what I'm trying to say is I think part of that's healthy, but really, and I guess I'm getting philosophical here, but really, you got to support it with evidence. And I think one of the challenges, especially in geology, where things are kind of abstract, geochemistry is a little bit better because it has that link to chemistry, that kind of quantitative, we can write chemical reactions to describe things, and we can test these in the laboratory and the experimental geochemistry side. But still, relative to what the chemists are doing, it's abstract. And I think in that abstractness comes this, in order to understand things, we kind of, there's a simplification, and there's also, for lack of a better word, there is I think, in some circles, dogma has an easier time in the geosciences than other areas,
sure,
because it's just, it has been said that it is this way. We've learned this, and it gets drilled into our minds. And you see this, editors, people who edit journals, get this all the time. You see these statements, and you get this back from the reviewer, or if you're a reviewer, so where are your references to support this? It's not to throw Reuter under the bus, but I mean, basically, people start with a really strong title, the non-colloidal origin of something. It's as well, where's your evidence for that? And if you provide it, then that's good. But a lot of the times people don't back up, big, strong statements with evidence, and that's that's kind of where we were at with this whole colloid argument.
Yeah, no, I totally hear. And I mean, in a different way, I've dealt with dogma for a really long time now in terms of a more of a mineralogical approach in some of the work that I've been doing. And it's just the hardest hurdle to overcome. So we definitely all need to be a bit more scientific in our work and first principles. What are we observing versus what are we supposed to know? Great point. All right, the paper that we chose to read is "The colloidal transport and flocculation are the cause of the hyperenrichment of gold in nature."
Mouthful.
It's a mouthful. Guys, for if you didn't know, I had to read that 3 times. What I'm going to say here is that while many of our listeners here are geochemists, although I've heard lately that we've now picked up some geophysicists, not many people are thoroughly overeducated on metal transport mechanisms like a lot of us geochemists, and particularly us Willy students. So before we delve into your research on the colloidal transport of gold, could you provide our listeners with a baseline as to why understanding metal transport is important in both a research and an economic geology standpoint? And in this question and in all things, you can be as specific and in the weeds as possible. Lately, we've been doing a lot of shows on exploration geochemistry and machine learning, so it's really exciting to be back here at the heart of academia.
Staying on the applied side of this, I mean, why is understanding the way you transport your metals important to understanding a deposit and exploring for whatever commodity you're exploring for? Well, I think the best example to give is if we think about solubility transport. So basically, if we're assuming that our metals are all transported, dissolved in solution in the hydrothermal fluids in your deposit. Now, especially these days, what is one of the most popular vectoring tools in at least in some, I'm obviously making a huge generalization here, but in many types of ore deposits, it might be hyperspectral core scanning. Look at your gangue mineral chemistry. What are your white micas telling you? Now, so this is very important because people that kind of, when I talk about, this links into the last thing we said. Point we talked about is to think about things really critically, and why are we just accepting this, or why are we doing this way? And at the foundation of looking at alteration mineral chemistry is one is assuming that the ore fluid that's flowing through those veins is altering the wall rock, and so you're looking at the alteration, the wall rock alteration, to understand the processes, the transport mechanisms that are happening to gain insight into what's going on in the veins. And to go a little more detail, you're trying to find specific processes that trigger the deposition of your of the metal you're interested in. So in the case of gold and other metals, boiling might be an important depositional mechanism. So you're saying, well, what does boiling do to the surrounding wall rock? How does it alter it? Are there things we can do? Because the thing about alteration is it's really, really widespread, right? So it's easy to go out and to the overused analogy, find a needle in the haystack. You can scan a ton of core. Most of the stuff you're scanning is wall rock. So it's, you can understand a lot more there than just by looking at the veins themselves. But the thing though is that that's, everything I just explained is built on the assumption, and yes, I'm picking, I'm staying on the colloidal track here, but it is, in fairness, it is the subject of today's paper, that is all built on the assumption that your metal is being transported in solution. So we're going to do this, and that the alteration in the wall rock is reflective of the ore depositional event. So you say, oh, let's go and try and find this if you're trying to, I don't know, I'm trying to think of a good example. If you epithermal to porphyry transition, you want to know kind of the routes you're looking for, maybe the illite to perophyllite transition, and you're trying to kind of position yourself within the hierarchy, and this certain white mica is characteristic of the boiling zone. And so we're going to go, map all that mica that's characteristic of boiling, and we're going to invest all of our resources there to explore because we think that's where all the gold is going to deposit. But what if you don't understand the process of that, of that deposition correctly? What if boiling is not causing that deposition? So that, that's why it's really critical to understand that part of the ore forming process, and how the metal is being transported, because it's basically driving your if there's other means at play, and we discussed this a little about the paper, and we can get into the chat later, then maybe alteration mapping isn't going to tell you anything about how, if it's, for example, if boiling isn't your trigger for depositing gold or copper or silver or whatever you're interested in. So there's my short answer.
No, I think it was a great short answer, just because, so I worked and still do work quite a bit in hyperspectral, and there's a lot of these now generalizations that we're looking for the transition from muscovite to phengite. And the question is, why exactly? And it's just because there's been a few papers written about it, but that doesn't necessarily mean that that's where, when you get towards the phengite, that's where you're going to find your copper. If anything, I found very few deposits worldwide where you do find your copper associated with phengite. And it's just because they're not asking the right question, and they're not understanding that transport mechanism well enough to make that call.
Well, it might work really well in one deposit where they wrote the paper, right? There's a lot of this too, that to kind of go back to the, I don't want to beat a dead horse here, but go back.
It's good to beat these dead horses.
Yeah. It's another issue with dogma is, and in this case maybe that's not a proper name for it. That's being overly, it's not giving it credit, because it might be good science in one deposit, and they've shown it, and yes, that muscovite to phengite transition is the sweet spot. But then don't just go take that to your deposit and say, oh well, just because this is in the same deposit bucket, it's in the same class of epithermal deposit or porphyry deposit, that we're expecting to find the exact same ore forming processes or metal transport processes. So don't constrain yourself by those things. Look at your own deposit.
But I think that's exactly it. And I think more people need to think of this in terms of the ore forming process, the metal transport process, and not just, okay, we're looking for this transition between these two minerals. And I think that's such an excellent point. And I'm really glad that people hear this. Yeah. All right, guys, so now we're going to jump into the paper. But first, what I really wanted to do was just, and it's not so much a quiz for Duncan as much as just to get everybody prepared for some of the stuff that we're going to be talking about. And we've already covered a few of these questions, so I'm going to skip over them. But really what I want to get out of the way first was just to get everybody onto the same page and just to ask some basic questions. And the first of those would be, Duncan, what's meant by physical-chemical conditions, oxygen fugacity, or what we see more often as FO2, as well as pH?
Basically, I came in I think, as I mentioned, my master's was mostly in structural geology, although I kind of flirted with this a little bit in throughout working for different companies. This was largely new to me when I started my PhD. So I can appreciate the need to define these terms, and why we care about them. So basically, physical-chemical conditions. And it's important just for everybody mixes this up, and anyone, Willie, our supervisor, just to have a quick aside about him, he always catches people doing this, and I've been guilty of it. It's not physiochemical, it's physico-chemical. It's easy, even your Word or Google or whichever spell check you have often gets it wrong. But physico-chemical is basically a basket term to describe all these different parameters that can vary in your ore fluid. So these are things such as FO2. So the fugacity of oxygen is essentially just the oxygen activity. If you've heard chemists in that. So basically the availability, I mean, I'm sure chemists are rolling over if I oversimplify this too much. But
oversimplify, please.
Yeah. I just think about it as the availability of oxygen. More oxidized environments are going to have higher FO2. I tie it into mineral chemistry. So the geologists, it's nice to just look at the formula of a mineral. How many oxygens are there? Are you going to have, you're like, oh, I got all these sulfide minerals, but here I have sulfate. So look, that's actually pretty cool. The sulfur is being an anion in the sulfides, and then something's causing it to be a cation somewhere else when it's a sulfate, right? Like gypsum. And that's because of if there's lots of oxygen around, presumably it's going to steal electrons and make the sulfur behave as a cation. So you see things like gypsum, it's typically tied with conditions of higher oxygen availability. And things, pH, I don't think needs a definition, but how acidic or basic are your ore fluids, and that all of these parameters in terms of metal transport. Basically, people who study metal transport, they look for a sweet spot. So there's all these different diagrams that plot FO2 versus pH or any of the other parameters that I've just mentioned. Activity of sulfur is another one. On those diagrams, there's basically, if you're looking for gold or whatever, based in part on laboratory experiments or thermodynamic modeling, there is a sweet spot where you can say we can dissolve the highest possible amount of gold or copper or whatever element at these conditions. So what are those optimal conditions for metal transport? And if we understand those optimal conditions, then we can take the next step and say where in the deposit we're trying to explore did those optimal conditions exist. And so you can get vectors from this kind of information. So I don't know if that is that.
I love that, and I especially loved how you finished that out and brought it back into both the sweet spot of transporting any kind of metal, and then also into, especially what's economic geologists would love to know, is how do we vector? And I think that's a really important thing to anybody listening here, that you can always reach out and ask us more questions about this topic that we're talking about now. I think you've done a really good job for now of just summarizing it, because that's all we want before we get into really some more of the meat of the paper. But it's all about understanding how you're moving metals from one place to another, and then that's a way that you can vector. And vector, I would argue, probably more successfully than just some of the standard dogmas say that you would usually use. And so that's why we love to talk about this stuff. One other T-ball question, and we've talked about it a few times, but I think it's important, especially in the case here, we're going to be talking about Brucejack, which is an intermediate sulfidation system. Can you just define for us boiling?
Boiling is a mechanism for metal, most commonly at least, a mechanism for metal deposition. So, and it's easy to confound the two. I mean, people talk usually about metal transport at conferences. How do we mobilize whatever we're looking for into these veins? Well, it's important to not oversimplify and remember there's really two important steps. One is you got to get the metals into the veins, either in solution or suspension. And then separate from that, you might move them around, and these obviously these are fluids circulating in a plumbing system. Separate from that is how do you deposit those metals? And boiling most commonly is a mechanism looked as a method to basically dump out your metals from solution. And so the magical thing about boiling is it's and there's other mechanisms. So one would be fluid mixing. You might have meteoric waters mixing with magmatic waters. But of all the different mechanisms out there, it is probably the most efficient to vary those physical chemical parameters that we just defined and described, to vary them very extremely. So, because whether it's dissolved transport or suspension transport of your metals, basically solutions or suspensions, they're happy, right? You need to disturb them to basically precipitate or flocculate. And by flocculate, all I mean is basically in the case of suspension transport, getting these little nanoparticles to aggregate. So what do you and by disturb I mean change one of those physical chemical parameters. So have a dramatic change in temperature, cool the fluid very quickly, change its pH, make it much more basic, change the oxygen, the oxygen activity, the availability of FO2. And the nice thing about boiling is it's like kind of like this magic bullet is it does everything that I just mentioned. Boiling cools the fluid so you can drop temperature rapidly. Boiling changes the pH. You boil off your hydronium ions and the FO2, and basically it changes everything. So it's very disruptive, and you can deposit a lot of metals through boiling, we believe, and so I think that answers your question, right?
It does. Yeah. No, and I love that, and I love how now we've also talked about this distinction between transport and deposition, which I think is also something that is underappreciated. We'll just go with that. And then moving on, and we've talked about this quite a bit, but I think it's just probably one of the last things I want to talk about in terms of simple things that I think will have a big impact, especially on our economic geologists that are listening. You talk here about the hyperenrichment of gold. We talk a lot in exploration about bonanza gold grades. So what do you mean about this hyperenrichment? And then how does this have a similar meaning, if so, to bonanza gold grades?
Very good question. Hyperenrichment, for without getting into very fine nuances, let's just say that it's synonymous with the word bonanza. It's bonanza is more of and it's, I think when we were writing this paper, I won't go through the whole submission. This paper is published in the Proceeding of the National Academy of Sciences. We submitted it to some other journals first, but one thing that we saw in reviews is that people, anyone who's not in, a lot of people who are not in exploration, don't know what bonanza. Bonanza is kind of a colloquial term, if you will, for describing really high grade gold. We all think of the prospector striking it rich, saying bonanza, but chemists and physicists and others aren't very familiar with it because it's not a term that kind of is batted around in their realm. So basically, to define it more fundamentally, bonanza is the bonanza grades are hyper enriched gold grades. I mean, there is no, and maybe listener will correct me if I'm wrong. We looked for, there's no formal definition by any kind of geological council for the term bonanza, but generally speaking, people think of bonanza grades as being in the hundreds, if not the thousands, of grams per ton or ppm gold. And perhaps you get bonanza concentrations of other metals too. So basically, how does the hyperenrichment of gold occur in nature is just another way of asking, how do we form bonanza deposits of gold in nature?
Now pivoting towards the actual paper, away from some of these definitions. Glad we got them out of the way, though. We keep talking about transport now. We've talked a bit about deposition. In the case of this epithermal system like Brucejack, starting from the magma chamber upwards, what is your proposed mechanism for the transport and deposition of gold? And in particular, what makes Brucejack different from other similar deposits?
It's a very, very good question, and I'm going to kind of I'll be upfront about this. I'm going to kind of give a political answer to it. Not answer the question very well. It's partly because we don't know. So. Brucejack, there are some unique things about Brucejack. One of them is that a majority of the epithermal veins, at least the electrum-hosting epithermal veins, so electrum is gold silver alloy for those who don't know, and that is the ore mineral at Brucejack. Most of the veins are carbonate veins as opposed to quartz veins. So that's slightly different from a lot of other bonanza-style epithermal deposits where everybody's looking for chalcedonic quartz and very, very quartz focused. So aside from that, though, I mean, Brucejack has a lot of similarities with other epithermal systems. It's in a sea of sericite, of white mica alteration, and there, we won't go into all the specifics there, but there are on the surface you see locally epithermal textures. There are a lot of things that make it look like any other epithermal deposit in the world. And the thing, though, is that we don't We've looked for evidence of colloidal transport at Brucejack as a way to explain the hyperenrichment of gold there. Others have looked in other deposits, but the groups are few and far between. So I mentioned Saunders starting this in the Southwest US. People have worked down there. And there's a group in Australia. I believe it's Laura Petrella. I think she's at, I hope I'm getting this wrong, University of Western Australia in Perth. They're looking at for colloids in orogenic settings. But these are, similar to us, maybe a group of 4, 5, 6 researchers and looking at one deposit or maybe 2 deposits. So I guess this is a long way of saying is colloidal transport might be happening it might be commonplace, but people haven't been looking for direct evidence of it. So we only have this handful of deposits, maybe half a dozen, where we have images of gold nanoparticles in the veins, and you can say, wow, this must be and it's not to say, just to be clear for everyone, solution transport and colloidal transport or nanoparticle transport, these are not mutually exclusive processes. You can have both happening at the same time in a deposit. Yeah, I mean, the answer to your question is we don't know. Is Brucejack, is it a super unique deposit, or is it, is this happening everywhere underneath our noses and we just we haven't appreciated yet. I guess, sorry, just the last thing, you could argue that Brucejack is somewhat unique in terms of there is very, very high grades there, but there are other bonanza gold deposits around the world. So even that kind of, it's hard to call Brucejack unique in that sense.
Thinking about one, I won't name it, but I'm thinking about this one very famous high sulfidation deposit. It was mined, mostly the supergene, for a very long time, then different layers of it. And then they got into the sulfide portion, and then they kept drilling down deeper into the hypogene, and they found, I don't really know how you would describe it, but this section of it that was just these bonanza style hyperenrichment of gold. They had no idea how to explain it, and it was probably just one of the coolest little things that I saw. Anyway, that's an aside, everybody. That's me reminiscing. So I think something that maybe our listeners would like me just to ask, just to clarify with you, when you say carbonate veins, you're not talking about carbonate infill, like later infill. You're talking about primary carbonate veins.
Yeah, so absolutely. I mean, there is, primary carbonate hosting electrum is what we see the vast majority of ore veins at Brucejack. That's not to say there isn't quartz in the veins, but we're thinking, it's not, even then, Brucejack's not unique. We see lots of, in epithermal systems, for example, manganese calcite, that pink calcite tends to be, usually it's not host to the ore, but there are, even then, there's a few, there's a deposit called Frutal del Norte in Ecuador that has a lot of carbonate and electrum. Some have suggested that it's an analog for Brucejack. But yeah, we're not talking about carbonate. We're not talking about Carlin style processes where there's carbonate replacement and there's secondary. That's one thing that we really, and we know this because we've looked on the nanoscale. It has been suggested before that at Brucejack that a lot of the carbonate is late, and quartz transported most of the gold. People have even suggested that quartz was the main matrix in which colloidal suspensions, these silica gels, were transporting colloids at Brucejack. But the thing is when we started making all these, so we made, in order to look for evidence of colloidal transport, you basically make these, I mentioned the transmission electron microscope, so you make these TEM foils. So they're basically thin sections for the TEM, and they're ultra thin. They're like less than 100 nanometers thick. They're thin enough so you can pass a beam, stream of electrons through the sample and image it that way. So rather than standard SEM, you're bombarding the surface of your thin section. with an electron beam, and then you're looking at basically the reflected or refracted electrons to generate an image and test your chemistry and all that. So on the TEM, you're passing electrons through, and that enables you to basically go down to that nanometer scale. So when we made these TEM foils, not only can you see, and if you read the paper, you'll see the images of the spherical nanoparticles, and I'm not going to go into super detail here, but you can get down to the level of seeing the atomic lattice fringes. So these are the edges of the lattice planes that make up the mineral, and anybody who took first year mineralogy knows that every mineral has a different lattice fringe spacing, so you can identify what it is. We identified these nanoparticles as gold. But separate from that, you can look at what the gold's sitting in. And everywhere we looked, the gold is sitting in calcite, not quartz. And so that's why we believe that this calcite is primary. So there's the long answer to your question.
And this long answer is perfect, because later on, which I no longer have to ask, I wanted you to describe some of these images, because guys, go read the paper, at least go look at the images. They're pretty spectacular. And some of his other work that he's done, he's got even more spectacular images. So that's another plug for you, Duncan. Pivoting a little bit, something else that I found really interesting about the paper is that we tend to talk a lot about seismic pumping in exploration geochemistry as a mechanism for getting the signature of a buried deposit to the surface. But I find it fascinating in your paper that you're describing it as a methodology by which the veins at Brucejack are becoming hyper-enriched in gold. So can you expand a bit upon this?
Seismic pumping, this idea that you have fault valves, right, that are opening and closing. It's a very common model for boiling. So just forget all the colloidal stuff people have been talking about for a long time in terms of solution transport and deposition models. Because of course, boiling is a very great way of precipitating stuff. So, but we envisage it somewhat differently, because basically, if you have a fault valve that's opening and closing, rather than that opening and closing of the valve due to seismic events, rather than that causing the precipitation of the gold and it staying there, we see the seismic pumping potentially as a ability to circulate flocculated colloidal suspensions. So basically nuggets. And you see, if you look at the paper, you'll see there's evidence of all these originally spherical nanoparticles. And then elsewhere where we look, we see these aggregates. So we've kind of frozen in time in these petrified, hydrothermal veins. We see evidence of the flocculation. And so you may be able to, if you can circulate suspensions of nanoparticulate gold, why can't you circulate suspensions of flocculated aggregates? And so it may be like that plug in your kitchen sink, that clot you might have when you have basically you think of grease or something, or milk is another good analogy. So milk is a colloidal suspension. It's fat particles. And when milk is happy and it's fresh, right, you basically pour it into your cereal, you don't expect to see any clumps at all. Because if you saw clumps, if you saw flocculated milk, you know it's going bad. And what that process is of milk going bad is basically the charges on the fat particles basically canceling each other, and basically you get curdling of milk. So imagine these curdles of gold in your hydrothermal veins, just as if you're pouring clots of milk out from your expired carton. You can transport these things. They can be in suspension in your fluids. And so maybe if you have a fault valve opening, an earthquake happens, you then circulate more fluids, you can basically move these clots along until other places where you can aggregate them into even larger clots. And so maybe your seismic pumping, rather than just being a way to open and close fault valves and boil, you're mechanically or physically transporting these clots to basically make them aggregate and have even bigger clots of gold, if that makes any sense at all.
It does, and it's so fascinating. Maybe I'm just a little bit spoiled. Oh my God, that's funny. But just spoiled because I've heard this twice. But listeners, have a listen to that part again because it will make sense. If it doesn't the first time, definitely the second time. On a related note, I love that you're not just talking about these macro vein features where we can physically see, and what anybody that stops by, well, now Newcrest owns Brucejack, so maybe at the next PDAG or Roundup, they'll have some core samples set out for Brucejack. But it's not just these huge aggregates of gold that you can see. It's also a lot of what Duncan has been talking about are these also nano scale features. So can you just chat to our listeners about how you investigated this and whether you think it could be an important in an economic geology setting? And I know that we talked a bit about what you saw when you were looking at under the TEM, but do you think that this is something important in an economic geology setting?
Great question. And I mean, to go back to a kind of earlier answer I gave, but in a different way, I mean, it really to drive home the point that we're really just at, this is the tip of the iceberg in terms of starting to investigate ore deposits at the nanoscale. And, we spent all of this session talking about colloids, but just in general, you think of any way that you're investigating your ore deposit, whether or not it's doing petrography, doing just even looking at drill core with a hand lens. Everything we've done kind of in the last 100, since the start of modern exploration, let's say last 50 or 100 years, we've kind of gone down to the micro scale. So obviously people have been looking at fin sections for a long time. I think SEMs have been around since just before the Second World War. So that we've been kind of, those methods, well, they've definitely advanced and been refined. There hasn't been a major new imaging method available to us. And I guess I'm talking about direct imaging. I know there's other, there's indirect imaging through looking at chemical core scanning and things like that, which are obviously huge advancements. But the TEM is really, there's the groups that I mentioned, they're looking for gold nanoparticles, but we can now go look at down to the atomic level almost at any question you're interested in your ore deposit. So it's a new frontier, and I don't think that's an exaggeration to say that. The applications are I mean, at this point almost limitless, because we're looking at one single process here. But I mean, if you wanted to understand other processes or just even to understand the distribution, if you have chemical anomalies in your white mica or muscovite or something like that, and is that occurring uniformly? Is that or if in mineral chemistry, is that a trace element you're so interested in, is that occurring in the mineral everywhere, or is that also occurring as a nanoparticle in that mineral? In which case, it's not going to be uniformly distributed. And so there's all these kind of questions that once you go down to the nanoscale that are opened up, and to be honest, they just haven't been really investigated thoroughly by economic geologists.
It's a great plug. And for all you listeners out there that are wondering what to do for your PhDs or masters, here you go. No, that's super interesting, and I really love that insight. So guys, to round out our discussion, I just have one additional question that I hope more than anything inspires our listeners. Duncan, can you just describe to us when you had your eureka moment and how you and the Willie group went from a typical bisulfite gold complexation to colloidal transport sand silica gels at Brucejack as your mechanism?
That's a great question, and to give credit to Willie, and sorry, people are probably going to roll their eyes when I mention the word dogma again. But
no, none of us are. We're geochemists.
It's being like, oh, that's the guy who just talked about used the word dogma 50 times in the interview. But to be fair to Willie, and a lot of credit is due here. I mean, he is a researcher. He literally has a paper 10 years ago that's titled "It's an Elements." Gold in solution. It's all about gold in solution. Willie has spent his career on trying to understand how you can transport and precipitate metals, gold especially, from solution. It's a huge step for him, somebody like him, who's had a career investigating a certain mechanism, and perhaps spewing some dogma himself, and then say, well, you know what, let's go look at something completely different, and it might even disagree with models we've proposed previously. And that's kind of exactly what happened here. I mean, the eureka moment, really, and I have to give credit to other people. We were not the first people to do this. Even here at McGill, I mentioned his name. There's a fellow by the name of Nick Harrikhausen who was looking for gold colloids. He had a different supervisor. He wasn't in the Willie group. His supervisor was a structural geologist by the name of Christy Rowe, and they were looking primarily in the quartz, and they did find limited evidence of nanoparticles, silver and some gold in quartz, but they didn't find at least good evidence, and by good evidence I mean images of thousands of these nanoparticles that are in these that are in the PNAS paper, and evidence for their aggregation, for flocculation. And so that's why the word flocculation really made it into the title of the paper, colloidal transport and flocculation. That's why it's so wordy, because there's this pressure when you're trying to get into these journals like PNAS that it has to be novel. So it's this idea that we have, yes, people have imaged nanoparticles before, but we are the first people to show direct evidence of the aggregation of the nanoparticles. And that's so important, because sure, you can have lots of nanoparticle suspensions, but how do you get from the 5 nanometer scale, so we're talking 1/1000th of a meter, 100,000 times thinner than the human hair, to, if you look at the paper or go pick up a piece of Brucejack core, to literally a baseball size, a fist size nugget of gold? How do you scale up? And that I mean, flocculation is the key driver of that process. So really, the eureka moment wasn't even seeing these nanoparticles. The first lamella we made, or foil, sorry, some people call them TEM lamellas, some call them foils, same thing. Let's just call it a section. We imaged on TM, and we found nanoparticles. We found some in calcite, and we said, oh, this is interesting, but people have seen this before, not the calcite bit. But then the second one we made, or maybe it was the second imaging session on the same foil, I can't remember anymore. We basically went to a different area of the section, and you can see, I think it's in the paper, if you're reading it, I think it's figure 3, if I'm not mistaken. We went to one of these there's lots of all these spherical particles, but then there's particles that have different shapes, they're bigger. And I think that this one in particular, Willie called it the steer's head, because it looks like a steer's head. And we were able to zoom in enough on it and just resolve. The TM's much more finicky than an SEM, depending on you pass electrons through. If things are too thin, you're not going to see those little lattice fringes. If things are too thick, you're not going to see those little lattice fringes. But in this one area of the steer's head nanoparticle, we were able to see that it was composed of multiple different lattice fringe orientations, and that's very clear in that figure. You can see, and basically the implication of that is that it's evidence of, because when you look at I should specify, when you look at the spherical nanoparticles, the 5 nanometer guys, you only see one lattice fringe orientation in the entire particle. So it's a particle there with it has with this crystal lattice, it's all uniform. But in the intermediate sized particles, they are aggregates of these individually what were originally individual or separate nanoparticles. And so basically this steer's head was I guess the eureka moment, if you want to call that. It basically was to our knowledge, the first at least convincing image where you can show this, and you can go all over. There's other particles like this too, where we have these masses of flocculated nanoparticles, and so that's the first step to scaling up to the fist-sized nugget of gold.
So interesting, so neat.
Well, thank you so much for stopping by the show. And thank you, all of our listeners, for listening to Geochemistry. Big thanks to Duncan for stopping by, dishing some very interesting, very different tea, and then taking us on this journey. Thanks to our sponsor, LKI Consulting, and to It's Water and Coma Media for our music. And if you want to learn more about the show, submit a request to be on the show, or recommend a geochemist to chase up, please go to our website at geochemistry.com and send us a message on our contact page. I'm looking forward to chatting with everybody next month, and until then, enjoy reading the next paper we have posted on our website.